Hello, so today we are going to do this problem, which is part of Leetcode Daily Challenge. Find the winner of the circular game. So we have n friends that are playing a game, and they are sitting in a circle, like this example here, where they are numbered from 1 to n, and we get the n value in the input. And we have this game that they are playing where we start at the first friend, so the one with number 1, and then we count the next k friends. We get the value of k in the clockwise direction, including this person, including the person we start at. So that means 1, 2. So that gives us this 2 here for k equal to 2. And then the last person, once we finish counting k, leaves the circle. So that means 2 here leaves the circle. And if there are still numbers, like in this case here, we keep going, but we start from the one after the number we just removed. So we start from 3. And again, we do include 3 in counting for k. And we keep repeating basically until there is only one element in the circle. And that element is the winner of the game, or that friend is the winner of the game. Okay, so for example, if we do the first example here, n equal to 5, k equal to 2, we start here, so 1, 2, so this person leaves the game. We start counting from the next one, which is 3, and so 1, and then 2, so 4 leaves the game. We start counting from 5, and so 1, 2, so this person leaves the game. We start counting from the next one, which is 3, so 1 and 2, so 5 leaves the game. And at the end we have 3 remaining, and that's the winner. So that's the idea. Try it with a bigger example just to get familiar with it, but if you look at the constraint, we have up to 500 for both k and n. So that tells you immediately you can do an O of kn solution. That should pass, because it would be like 25, right? Multiplied by 10 to the power of 4. Okay, so that should pass. Even n squared should pass as well. So how do we do that? Okay, so let's see how we can do this. So let's say, for example, let's take that first example, n equal to 5 and k equal to 2. So we can just simulate what the problem is asking us to do, except how do we represent these circles here? We could just have them in an array, right? In an array, but to accomplish the circular behavior, we can just use modulo, right? So we can just increment, but each time do modulo n to get to the next one. Okay, so that should be straightforward. So for n equal to 5, we know that we will have, let's call it a circle. It would be an array, but just conceptually we'll represent it as a circle. With the indices, we will do modulo. So that would be 1, 2, 3, 4, 5. Right? That way we have 5 elements. Okay, so what can we do? Well, we need to keep removing until we have only one element in the circle. So that means already we will need to keep going until circle has one element. And then if it does, then we can just return that element. But what should we do here? Well, here what we need to do is remove, okay, starting from last one, from the previous iteration, remove the friend at k, right? That's what, after counting k, that's what the problem asks us to do. And so already you can see we need to keep track of the last one from the previous operation. So let's have last. Now initially we start at the first friend, which is equal to 1, but just because we have a list where we will index, the indexing starts from 0, we will just index starting from 0, right? So this last would be 0, but it's still pointing to 1, okay? And so here, to get to the kth friend, remember we include this one in counting. So to get to the kth one, we need to add k minus 1, right? Because our indexing starts from 0. So it needs to be k plus k minus 1, because we include the element itself. We include the 1 itself. So in this case, with k equal to 2, it will be plus 1. So it would be just this 2 here, which is exactly what we have in the example, right? Okay, so this needs to be the new last value that we need to remove. Okay, but we need to do modulo length of the circle, because what if k was, let's say for example in this case, what if k was I don't know, maybe 5, right? So we would be adding to 0, we would be adding 4. So it would be here, but what if k was 6 actually? Then we would be adding 5 to 0, and so 5 would be out of bounds, so we need the modulo to have 5 actually pointing to this one. And in reality, since this is a circle, this is the next one for 5, right? For the value 5. Okay, so that this modulo here will take care of making it like a circle. Now we need to remove the element at this position because that's the element after counting k, and so we need to have circle and then remove the element at position last. Now since we removed this element, we don't need to increment last, because now last is, let's say for example we landed 2 here. So when we land at 2 with k equal to 2 here, we remove 2. Now when we remove 2, now the index here is 1, it's 2, and this is 3. So now last is pointing to 3, and that's exactly what we want. We want to start the next one from 3, start counting from 3 to get to 4 and remove 4, right? So this would work, so we don't need to update last. And that's pretty much it. That's literally just applying what the problem asks us to do. And so let's just copy the code that we have. And we need to define, of course, circle. So circle is just the numbers from 1 to n. So in Python, we need to do n plus 1, like this. Okay. And we remove the element. So if I run this and submit, it does get accepted. Okay. So now what is the time complexity for this solution? Well, the time complexity here, we know this loop, each time we remove one element. So we know it definitely runs n times, okay, in the loop. But what about each iteration? What happens? Well, in each iteration we do a remove, and remove takes O of n time to remove from a list. So this operation alone is n, O of n. And so O of n by O of n, that means the entire algorithm here, the entire implementation is O of n squared time. Now in terms of space, we are using this circle array, which is of length n, so we are using O of n space. Okay. Now can we do better? The problem here asks us to do in linear time with constant space, so O of n time and O of 1 space, but that's a little bit harder. So let's first try to get to just anything smaller than O of n squared. I think we can do definitely nk. We can do nk time. That's very close to, that's almost like O of n squared because they have the same bounds, but still I think it's a useful thing to try, so let's try it. So a way to think about this is, let's think about what data structure we can use that can help us make this easier. So if we have something like this, right? What are the operations that we need to do? Well, we need to remove easily, right? And we need to get to the k friend, counting k friend easily. Those are the two things we need to do. So what if we just make this be a double-ended queue, right? Okay. If we do that, what happens? Well, k equal to 2. So we can, on each iteration, we can just move all, basically do k times, do the following. Take this one here, move it to the back because it's not the one we want to remove. And then we have 2. So we need to do that basically k minus 1 times because we are including the element itself. And so now we are at 2. This 2 is what we need to remove. And in a queue, to remove, you just do pop left. Okay? But to take one from the front and add it to the back, well, that's just k append you append the element that you move from the front. You move it from the front, you append it to the back. And so to append to the back, this we need to do it k minus 1 times, because we want to keep the kth element so that we remove it here, right? Okay, and we keep doing that. So we remove 2. Now our front is 3. So we do this again. We need to do k times, so not 3. So 3 we take it and put it to the back, and we remove 4. Okay, so remove 4. And then same thing happens. 5, we put it, move it to the back, and then we pop 1. 3, again, we move it to the back, and pop 5. And now we are done. So we do this while there is while there are more than one element. Okay, and then at the end we can just return the remaining element. Okay, so pretty straightforward when you use a queue. It's, I think, even easier than the indices. So let's just run this. So what we need is something like this. Now our queue initially needs to have the elements I for I in the range of 1 to n plus 1, similar to the circle that we had. So if I run this, let's see, this needs to be a double-ended queue so that we can append to the back and pop from the front. Okay, so that gets accepted. Let's submit, and it gets accepted. Okay, so now in terms of time complexity, what is this solution? Well, we know each time we pop, at least we pop from the queue once. So each time it reduces by 1, and the queue's length is n. So we know we have n iterations here. Now for the inner loop, we know it runs k times, and each of these operations is constant. Append and pop left are constant for a DQ. So this here is k times, and so the overall time complexity is of nk. And space is still of n because of this. Okay, so I think this one is easier to implement and visualize, but it's still pretty similar time complexity and space complexity. So how do we improve that? Okay, so there is another way to do this, which is recursive, that may get us closer to constant of n time and constant space, and that's the first thing to notice is what's expensive in this queue solution. Well, what's expensive is having to actually move the elements to the end so that we can remove the front, right? And so a question you might ask is, what if we just not remove and just are able to find the value without removing anything? So that's the first insight. But if we want to try the recursive solution, we need to think about what are the smallest subproblems and how do we reduce the parameters of those subproblems. Okay, so first, a couple of things to notice. If you look at the original array, the original queue that we had here, what happens each time? Well, each time, on each iteration, which by iteration I mean counting to k and then removing the kth one, what happens is we put 1 to the front, and then we remove the kth element. So what happens? So before this operation, we had this list. Now afterwards we have this list. What's the difference between the two? Well, this one was of some length n. This one is reduced by 1 because we removed that element, so it's of length n minus 1. So already in our recursive function, we can know that, let's say, when we are calling n with some parameters on n, we know that the recursive call is we are going to pass n minus 1 because an element needs to be not counted for. Now we need to know whether we are going to remove it or how do we handle it. Okay, so that's the first insight. Now what is the second insight? Well, the second insight is that what happened here for 1? What happened? So let's look at the indices for a second. So we had 0, 1, 2, 3, 4, 5. 1, 2, 3, 4. Okay, so now the index is 0, 1, 2, 3. So this is 1, 2, 3. Okay, 1 was at index 0, but now is at index 3. 3 was at index 2, now it is at index 0. So what happened to 3? Well, 3 moved from index 2 to index from index 2 to index 0. So basically for 3 we did minus k. K is equal to 2. Okay. So basically, and that the same thing happened for every other value, for 3, for 4, and for 5. Each of them, so for example, 5 moved by 4 minus 2, which is 2. Okay, so each one of them moved by minus k. Okay, so each index moved by minus k. Now you may say, okay, what about 1? Because 1 is actually now at index 3. So 1 was at index 0. So I'll say 0 minus 2. That gives you minus 2. Okay, now what about if you do minus 2 modulo the length of the array, right, which is, let's say, 5. So if you do minus 2, so modulo the length of the array, because minus 2 is not a valid index, but to get it to be a valid index, we do modulo n, which is, at this point, n was 5. Then that would give you 3, which is the exact index where 1 is at. So we know that this is what's happening for every element. Okay, so how do we do that without actually manipulating the array? That's the question. So this is what happened in the new indexing if we had actually removed the elements. But since we don't want to modify the array, we just want to, from these indices, we want to get back to this. Okay, and so let's say from index 0 to get back to this, well, we just add 2, we just add k, right? I know this is a little bit counterintuitive because we first assume we did the movements and then we want to get it back to the original list index. And so to get it back to the original index list, we just add k, right? And so the recurrence here is that we want to add k, right? But we still want to do the modulo for n for cases like the 1 value here. And so we still want to do modulo n. So this is what we return. Now, of course, we want to keep track of k, so you can either make it as a self variable or you could just pass it. Okay. Now, when do we terminate? Well, we terminate when there is only one element left. That's what the problem asks us to do. When do we have only one element left? Remember, this counts how many elements are remaining that we haven't removed. We don't technically remove them here, but we eliminate them. And so if n is equal to 1, that tells you we are done. Now what should we return in that case for n equal to 1? Well, we should just return 0. Okay, because if we return 0, it won't be actually the exact value 0, because it will return to the caller, and the caller will add k as many times as we need to so that we get to the actual index in the original array, right? Okay, but then remember, here we return 0 because I'm assuming we start indexing from 0. But since we want to get the values, let's just add 1 to account for the fact that we are starting to index from 0. So when we call recurse on n and k, so the first call to this function, we just want to add 1. Okay, and that's pretty much it. It's very tricky, this thing where we assume we had moved but then map back the indices to the original array is very tricky, but just try it a couple of times. I think it will be clear. Okay, so let's just copy this here, move this to our solution, and this would mean basically that that we need to call this. Okay, so we need to call this like that, and then we return this value. And that should be it. So let's run it. Let's submit. and this gets accepted. Now, in terms of time complexity, what is this? Well, this is O of how many times does the recursive function run? Well, you can see each time we subtract -1. So at most it will run n times. Now, what about space? Well, you can see here this recursive function also, the depth is n, and so at most in the stack we will have n calls, and so O of n space. Okay? Okay, so how do we think about the iterative solution in this scenario? Well, let's just take this formula here and write it in terms of a recurrence relation. So f of nk here basically is equal to f of n minus 1k plus k modulo n, right? And so to do this in an iterative format, now of course there is the base case where we return 0 basically if n equal to 1. F of nk is equal to 0, right? So the way to do that, well, with this is basically let's just compute bottom up, where basically let's compute first for n equal to 1 is already a base case, so we know it, its value is 0, but let's compute for 2. Then let's compute for n equal to 3, and then let's compute for n equal to 4, all the way until we get the value of n. Now, just to avoid confusion, let's just call these i's. So I equal to this, I equal to this, and then we compute for I equal to n. And since for I equal to n, we already have for I equal to n minus 1, it should be easy to just apply this formula because the value would be available, right? It would be just the previous value we have. So that's the key insight here. And so to do that, well, we need to just do for I in the range of, we said we want to compute from 2 to n. So 2 to n in Python, it needs to be +1. Now, what is the value for, let's call this f, for, this is for n equal to 1, okay? Now, remember, I here is equivalent to n, so that means, let's just apply this. So this new value is just the previous value, which whatever f was, plus k modulo n, but n is actually I in this scenario, right? Because each time we have a different value so that we can get to n. And then at the end we just return f, but remember, in the same way here in the recursive call we had to add +1 for the index because we start at, because it counts from 0, we need to just add +1. And that's pretty much it, and it gets accepted. Now this solution here, this is O of n time, okay? So it's O of n time. Now, what about space? We are only using this variable, right? We are not using a table, we are not using a recursive function call, so it's O of 1 space. And with that we get to the what's being asked of us here. I hope this was clear. Thanks for watching, and see you on the next one tomorrow. Bye.